I'm Daniel, and this is a joint work with Maurice Heymann, Benny Pinkas, and Thomas Schneider, my advisor. I also thank you for joining the third talk on PIR in this session. So we have seen single-server PIR, we have seen multi-server PIR with an offline phase, which can be used to get speed-ups in the online phase. And now in this work, we even go one step further and make the offline phase completely independent of the client. So this means the PIR server do not even need to know the clients before they can compute the offline phase. So we have many applications for PIR. So basically, the most important one is in the area of private set memberships, where we can securely check if an entry exists in a public database. Like for instance, if we take some patent databases, we can check if our patent that we have developed the idea is already in such a database. And we can use PIR to not leak which patent we actually have. And some other areas for PIR are in the area of private messaging apps, where we can hide the metadata in the messages we send. And another important application is compromised credential checking, which is also part of the private set membership area. But here, we want to check if our credentials were already leaked in a data breach. And by using PIR, we can completely hide our credentials from the servers. So in this work, we also focus on multi-server PIR, where Alice communicates to at least 2 servers. And usually, in all standard PIR protocols, Alice first sends a query to each of the servers. Then the server locally do some computations, and then send their answer back to Alice, who then can combine this answer to the desired database entry. A drawback of this model is that we need to assume that these servers, or a subset of the servers, are non-colluding. But the big pro of this is that this is very efficient, because we do not really need to rely on expensive operations like homomorphic encryption. So the ideal functionality in classic PIR protocol looks like this. So the setting is Alice has an input ID X, which is the index of the database item that she wants to query. The servers share a database, which is assumed to be public. And in the end, Alice wants to learn the desired database entry on her index. So first of all, she computes a request for each of the servers. And usually, this is a B-bit, 0-bit string with just a single 1 at the position of her index. So these n queries XOR up to this bit string. The queries are then sent to the servers, and the server locally compute the answer. And this is usually computing the query with the database and XORing these things up together, sending back the answer to Alice, and Alice can then combine these answers by XORing all the blocks together and gets the result. So the drawback, which we also saw in the last talk, is we need to access the whole database in the online phase, and that's not what we actually want, because it's too expensive. So in this work, we look on so-called client-independent preprocessing, which allows preprocessing independent of the client. And we look at some old scheme that's called RAID PIR. I want to briefly introduce you this. So in RAID PIR, the database is built up into multiple blocks. And these blocks are again split into multiple chunks. And usually, the number of chunks is equal to the number of servers. So we have 3 servers in this example here. Then the idea is that the main query, which is denoted as a big Q here, that this is the 0-bit string with just a single 1 at the block number 5. So in this example, we assume Alice wants to retrieve block number 5. And the idea is that now these 3 queries XOR up to this main query. And now the client can choose this query as follows. In the purple cells, the values are generated randomly. And only the orange cells, which we call the flip chunks of the servers, they are computed by XORing these columns together. So now, as most of the query is chosen randomly, we can also use a seed for it. We choose a 128-bit seed for each query, put them into the pseudo-random generator, and this can expand this query to whatever size we need. So even if we have thousands or millions of blocks, we don't need to choose or to transfer so many bits separately. We can just use the 128-bit seed and can expand thousands or millions of bits. So in RAID-PIR, the client chooses the seeds, and we'll now look at what happens when the server chooses the seeds. And when the server chooses the seeds, the server already knows a huge part of the query. So basically, n-1 over n of the whole query is expanded by the seed. And this is information the server then knows independently of the client and can be computed in an online phase. And consequently, only 1 over n, which builds the flip chunk of the query, is known in the online phase. So we only need this information from the client to compute the whole query. So the CIP-PIR model now looks as follows. We have basically the same setting. Alice inputs her index. The servers share a database, and we want to learn the database item on the index. Now we also assume that the servers have a queue with deed value pairs, which are generated in the preprocessing phase without any interaction with Alice. So in the online phase, the first step is that the servers pop one of the seed value pairs and sends the seed to Alice. Then Alice computes the request, choosing the seed received from the server instead of choosing the seeds on her own, sends the query back to the servers. The server computes the response using the preprocessed value AI from the queue, sends back the result to Alice, and Alice can combine these together to receive the desired database entry. So basically what I've shown you is the basic of our new protocol, which we call CIP-PIR. And I want to highlight one cool feature of CIP-PIR, which allows for very efficient batch preprocessing. So instead of computing the seeds one by one, we can group them together into a T seed. And we expand this T seed together so that we can compute T queries independently. And the good thing is, looking ahead, when we deploy these on a GPU, we would have many very expensive shifting operations when we want to shift the database parts into the memory of the GPU. And we can compensate these costs and amortize these among all the T queries that we compute in parallel, though the preprocessing is not so expensive anymore. And finally, what we have then, after a couple of time, T seed value pairs, which we can use in the online phase. So our next contribution is some database compression techniques in PIR. We basically have two techniques for this, and I show you. So the first one is that we use shorter hashes. So this is basically optimizations for hash-based databases, which are often the case in these private set membership applications that I've shown you. The idea is that we only store omega plus logarithmic n bits of hash values. And here, omega is a statistical security parameter, which we can choose so that we are fine. And the number n is the number of entries of the database. And then we have a different sequence. So we assume that the database is sorted. Like if we have hash values and we have thousands or millions of hash values, then these are very close together. And if we subtract neighboring hash values in the sorted database, we would have many zero prefixes. And obviously, we don't necessarily need to store these zero prefixes. And instead, we just store the differences of neighboring items so which gives us an improvement of factor 3.3. Then we finally also implemented our protocol, and we provide two implementations for it. One is based on a CPU, which we do some optimizations, like also parallelization via OpenMP. And the more interesting one is our GPU-based implementation. So I want to show you some results here. So as the baseline for our evaluation is FSS-PIR, which is PIR based on function secret sharing, which basically has the same types of operations, but it decreases the online communication complexity to logarithmic, while in CIP-PIR or in RAID-PIR we have sublinear communication complexity. So the gray line is FSS-PIR. We re-implemented it also on the GPU to have a fair comparison, so we have exactly the same setting here. And this is the gray line. And the first benchmark is the online cost of our CIP-PIR, which is the green line, so excluding the offline phase. And we see that CIP-PIR is already better for databases starting at 8 GB. Then interestingly, the blue line is now the amortized total cost, like including the online phase and the preprocessing phase. And for our benchmarks databases up to 25 GB, we don't beat FSS-PIR in the total cost, but we see a clear trend that these two lines get closer and closer, and we even expect that for larger databases, CIP-PIR would also outperform FSS-PIR, including the total costs. So in summary, what we did in this work, we designed a new PIR model, which is called Client-Independent Preprocessing, and allows preprocessing completely independent of the client. We designed a protocol called CIP-PIR, which also allows very efficient batch preprocessing, apply some database compression techniques in PIR, and implemented everything on a CPU and GPU. An interesting future work would also be to apply the CIP model to FSS-PIR to also benefit from the logarithmic communication complexity. So we have code for this, and with this I want to conclude my talk, and thank you for your attention, and I'm happy to get questions from you.